introduce our third speaker of the school, which is Professor Shiraz Minwalla from TIFR in Mumbai.
Thank you. Okay, so my lectures are titled Fluid Dynamics and Gravity, and are going to be about the connection between the equations of hydrodynamics, the equations of fluid dynamics, and the equations of Einstein gravity in the context of the ADS-CFT correspondence. Okay, the lectures are structured roughly as follows. The first two lectures will be about fluid dynamics and will contain almost no mention about gravity. Okay, and the remaining two lectures will be about the relationship between gravity and fluid dynamics in the context of the ADS-CFT correspondence, and what we can learn from that. Okay. Now, so let me start immediately by just introducing fluid dynamics or hydrodynamics. Okay. So, by the way, you might wonder why I want to spend, why I'd want to spend two lectures on fluid dynamics, because this sounds like an old classic subject which all of us should have learnt about in our undergraduate days, and you shouldn't have to, in an advanced school, spend two lectures on hydrodynamics. The reason I'm going to spend two lectures on hydrodynamics before turning to the connection with gravity is that this old classic subject remains pretty badly understood. Okay, there are many basic questions about hydrodynamics that, as far as I know, the answers to which, as far as I know, are not well understood. These questions are not about complicated behaviors like turbulence and so on. Those are, of course, important deep questions about the behavior of nonlinear differential equations. These are much simpler questions about the structure of the equations of hydrodynamics, the kind of question a theorist should be able to answer even if he can't solve the equations. Okay, so a lot of my first two lectures will be about general constraints on the structure of the equations of hydrodynamics, and then we'll turn to see what gravity has to add to the story. Okay, so the first question is what are the equations of hydrodynamics? Well, the equations of hydrodynamics start with the observation that in realistic situations, if you take a system that has conserved charges, a conserved energy and a conserved global U1 charge, for instance, you start that system off in an arbitrary configuration, you wait long enough, and if the field theory that you're looking at is not unnaturally special, it's not an integrable field theory, okay, then the system equilibrates. So you wait long enough, no matter what you start with, the system equilibrates, and the properties of equilibrium are described by the equations of by the formulas of statistical mechanics or thermodynamics, and in particular much simpler than specifying the full state of can be specified much more simply than specifying, say, a full quantum state of the field theory, which requires you to know all its degrees of freedom and so on. It can be specified in rather general terms by specifying a partition function that depends on maybe two numbers in the example I told you about, namely a temperature and a chemical potential. Okay? This is already a marvelous fact that we're all used to and we take for granted, but it's quite amazing. And this is the starting point for the analysis of hydrodynamics. Okay, now, in order to motivate the study of hydrodynamics, you might ask for a slightly more detailed question about what happens when you take a system, hit it, and let it move. The question you might ask is, since I can describe the properties in equilibrium in such a beautiful and universal manner, is it possible that I can describe some aspects of the approach to equilibrium in a comparably beautiful and universal manner? And the answer is yes. In some situations, the answer is yes, and it's achieved by the equations of hydrodynamics. So, the basic idea behind the equations of hydrodynamics is that if you've got a system that is not equilibrated, but is sort of locally equilibrated. Okay, so suppose I've got a system that's very big, and in little patches, any little patch of the system is more or less indistinguishable from a little patch inside a globally equilibrated thermal ensemble. Okay? So suppose you've got such a system, and these little patches, as you move around, are all equilibrated, locally equilibrated, but the parameters of this equilibration change as you move around. Okay? So this little patch could be at temperature T1, this little patch could be at temperature T2. Okay? This little patch could be at chemical potential mu1, well, this is at chemical potential mu2. Okay? In such a situation, since each local patch is sort of equilibrated, you might think that you shouldn't have to refer to all the degrees of freedom of the field theory in order to describe the subsequent dynamics of the system. It should be enough to refer to the degrees of freedom of thermodynamics. Okay? So now what were the degrees of freedom? What were the parameters that specified thermodynamics? So let's stick for the first few minutes, for the first half of the first lecture, with a very simple system. We're looking at a system whose thermodynamic equilibrium is characterized by two numbers, a temperature and a chemical potential. Okay? So the kind of system we're going to be studying are systems in which you can characterize the system by a varying temperature field, a varying chemical potential field. But that's actually not enough. That's not enough by itself because if you've got an equilibrated system, you can take that equilibrated system and boost it to look at an equilibrated system moving at some velocity. When we study thermodynamics, we don't usually do that because all the properties of the boosted system can be recovered from the properties of the unboosted system merely by a boost. However, now we're looking at systems where little patches of which are in equilibrium at different value of equilibration parameters. So these different patches could be moving at different velocities. And while the overall velocity can be removed by a boost, the relative velocities cannot. Okay? So in order to study these locally equilibrated systems, I need to specify also the fore velocity as a function of x. X for me denotes both space and time. Okay? Space-time coordinates. Okay? So in such a situation, in a situation where things are varying slowly, okay, the effective degrees of freedom of the system in order to specify subsequent dynamics might plausibly be regarded as a temperature field, a chemical potential field, and a velocity field. Okay? This is the basic idea. This is the first important basic idea of the equations of hydrodynamics, of the hydrodynamic system of description of a system. Okay? Now, I'll come back in a minute to say what I mean by slowly varying compared to what. But before we do that, let me turn now to a formulation of the equations of hydrodynamics. What we've done here is to specify what the variables of the hydrodynamic description are. That's huge progress. They're very simple variables. There's no F squared field if we're dealing with QCD, just temperature, chemical potential, and U mu. Okay? But that's progress, but it's not complete yet, because we need, in order to be complete, we need to specify the equations of hydrodynamics. Okay? How many fields do we have? If we were in 3 plus 1 dimension, well, let's say we were in, Subir wanted capital D, which is equal to little d plus 1 dimensions. Okay? Okay? So now let's count the number of degrees of freedom in our variables. There's 1 for the temperature, 1 for the chemical potential, and can somebody tell me how many for the velocity field? Is it capital D or little d? Little d. Although mu runs over capital D indices, this field here obeys the normalization condition u mu is equal to -1. So it's one constraint, so there are actually only little d degrees of freedom. As many degrees of freedom in a relativistic as a non-relativistic velocity. Okay? So the total number of degrees of freedom is little d plus 2, which is equal to capital D plus 1. Okay? So we need capital D plus 1 equations to specify the evolution of our capital D plus 1 fields. What could these equations be? Well, let's think of some equations. The kind of description we're searching for is very general and universal. So let's try to think of some equations that very generally and universally apply to any quantum field theory. Okay? Thinking about that for a minute, you immediately come up with the answer. any quantum field theory, okay, obeys conservation of the stress tensor. Okay, and I'll soon modify this equation to account for the presence of background fields, but let's start simple. Any quantum field theory that has a conserved U1 charge also obeys conservation of the charge. How many equations do we have here? Well, that's D, capital D, just little d plus 1. Okay, how many equations do we have here? That's 1. This is D equations because there are the free index can vary over D values. Okay, so that's as many equations as variables. Great. We've identified our variables, we've identified our equations. That sounds like progress, except we're not yet done. We're not yet done because these equations are equations for the stress tensor and the charge current. The variables are temperature, velocity, and chemical potential field. That doesn't go. What we need are equations for the temperature, velocity, and chemical potential field. How do we get that? Well, we get that if we can somehow take the stress tensor and express it as a function of the temperature, temperature, chemical potential, and velocity fields. Similarly for the charge current. Okay? This process, expressing the stress tensor as a function of other fields, of these thermodynamic fields, similarly for the charge current, has a name. The expression for the stress tensor in terms of thermodynamic fields is called the constitutive relationship of the stress tensor. Okay, similarly for the charge current. Now something I want to stress is the following: the basic idea of the hydrodynamic limit. The basic idea of hydrodynamics is an effective long wavelength field theory. You see, why is that? Okay, sorry, I should have said first, what is the physical principle that should allow us to calculate T mu nu as a function of chemical potential, temperature, and velocity? It's a local equilibration. Because the stuff is locally equilibrated, approximately we already know what it looks like, what the stress tensor looks like, because we understand global equilibration. And then we have to correct that. Okay? So now, because the basic principle of hydrodynamics is this local equilibration, okay, that idea in itself tells us that hydrodynamics is an effective long wavelength theory. How does it do that? Look, you see, as I mentioned, what we want to try to do is to think of any given patch of stuff as approximately thermally equilibrated. Okay. Now there's a length scale associated with equilibration. You can think of this length scale in an example of dilutely colliding molecules in a gas. This length scale would be perhaps called the mean free path. Okay, but we're going to abstract this notion that there's a length scale associated with equilibrium. Things need to collide around over a certain length scale or over a certain time scale in order to equilibrate. Now, if the temperature of the system changed from T to T by 2, for instance, over this length scale, then you cannot reasonably assign any temperature to the system. Because in order to assign a temperature to the system, you need to look at it over the equilibration length scale. If the temperature changes significantly over that length scale, it's not approximately thermally equilibrated. Okay? So, the very idea of hydrodynamics works only in the limit in which the length scales of variation, which I'll call delta x, you can measure these by taking the derivative of a field and dividing by the value of the field at that point, inverting that. Okay, so the length scale over which things vary is much, much larger than the mean free path, or the local equilibration length scale associated with that thermalized fluid at that point. Okay, so that tells you that hydrodynamics as written is a long wavelength expansion. Okay, the equations of hydrodynamics should not apply exactly, they should only apply in a derivative expansion. Therefore, these constitutive relations that we want to write down that express the stress tensor as a function of other fields should similarly be written in a derivative expansion. Okay, it should be written in an expansion of derivatives of the basic thermodynamic fields. Okay, this is both convenient, as we will see. It will allow us to use symmetries to categorize what you can write down, but it's also conceptually sufficient. To try to do more, to write down an exact expression for the stress tensor as a function of thermodynamic fields is stupidity. Okay, it's trying to apply effective field theory in a domain where it doesn't work. Okay? So the hydrodynamics is should only be thought of as a derivative expansion. Okay, so what we're supposed to do in order to close the circle, in order to find complete equations of hydrodynamics, is specify what T mu nu is as a function of thermodynamic fields, order by order in an expansion in derivatives of these fields. Okay, so let's start with the leading order in the derivative expansion. The leading order in the derivative expansion is the 0th order. At 0th order, an expansion in which you cannot, if you have no derivatives, you cannot distinguish a constitutive relationship of a perfectly equilibrated fluid, uniformly equilibrated, from one that's only locally equilibrated. So we know the answer for this. T mu nu at 0th order in the derivative expansion is whatever comes out of thermodynamics. And this, all of you know, you get the energy density, let me call it rho, into u mu u nu, plus the pressure into, let me write this, rho plus p into u mu u nu, plus the pressure into eta mu nu, where my signature conventions are eta mu nu is equal to minus 1, 1, 1, 1. Okay, and J mu is simply the charge density times u mu. Okay, now some of you are thinking this doesn't look like much progress. Again, you've introduced new variables, the energy density, the pressure, and the charge density. We wanted everything in terms of, let's say, a temperature field and a chemical potential field. But you see, because of the idea of local equilibration, you can write the temperature, the pressure, the charge density, and the pressure, the energy density, and the charge density as a function of chemical potential and temperature fields using the formulas of thermodynamics. Okay, so if I tell you what the pressure of the system is in equilibrium, I tell you what P of T mu is. Okay, so it's specified. Okay, when you use the formulas of thermodynamics to determine what the charge density is as a function of T and mu. So for instance, for the charge density is simply Q is equal to del P by del mu. Okay, so just take this function, whatever it is, you get the charge density. This is a similar formula for the energy density using the formulas of thermodynamics. Okay, so all of this expression here, though it doesn't look like it, is actually expressed as a function of local temperatures and chemical potentials. Okay, and in order to complete my specification, to tell you what my exact equations of hydrodynamics are, I have to specify one function for you, namely the pressure as a function of temperature and chemical potential. Everything else is specified in terms of derivatives of this object. So the ambiguity in the equations of hydrodynamics at first order is an ambiguity of one function of two variables, and you can break that ambiguity by specifying the equation of state of the system. You know the thermodynamics of the system, you know the equations of hydrodynamics at 0th order in the derivative expansion. Okay, excellent. Now, we're effective field theorists, or we're not satisfied by looking at a leading approximation unless we can systematically correct it. Okay, so we want to know, and actually, at least at first order, there's very important physical reasons to systematically correct this expansion, to go beyond the leading order. Actually, the physical reason turns out to be that these equations do not account for a very important fact of the behavior of hydrodynamics, namely dissipation. These equations are the equations of what I call perfect hydrodynamics. Now, non-dissipative, real fluids, in any for any real system or any real ideal quantum field theory, These equations are modified in a way that qualitatively changes the behavior of hydrodynamics. It introduces dissipation. Okay? So at least to first, and for other reasons to second order, we want to understand, even for practical purposes, how these equations are corrected. And being effective field theorists, we want to understand the principles to correct these equations to all orders in the derivative expansion. That's when we'll declare we have full control over the equations of hydrodynamics. Okay, so we're not satisfied with specifying things at first order. So what we want to do is to specify them arbitrarily. So the stress tensor, so let me call this guy T mu nu perf. Let me call this J mu perf. Okay, so what we're going to do is to specify T mu nu is equal to T mu nu perf plus some correction term which I call pi mu nu. Okay, and then J mu is equal to J mu perf plus some correction term which I call J mu dis. This is actually a very unfortunate name because we will see that some of the terms in J mu dis are in fact not dissipative. But it's a standard name, so I won't try to change it. Okay. Now pi mu nu and J mu dis by their nature are contributions to the stress tensor and the charge current as functions of the chemical potential and temperature fields that are of first or higher order in derivatives. Pi mu nu and J mu dis are can themselves be graded in a derivative expansion. Okay? And specifying what pi mu nu is and what J mu dis is to any order in the derivative expansion specifies the equations of hydrodynamics to that order in the derivative expansion. Yes?
I thought dissipation was the idea that energy wasn't conserved, so therefore my divergence list of the stress energy tensor I thought you'd correct rather than...
Yes, so since energy is always conserved, that's the point you're making. In this nice relativistic context, you see dissipation is really the transformation of kinetic energy into heat energy. But in our nice relativistic stress tensor, we count all energy. So energy is always conserved. Okay, the way to think of dissipation is as a process that leads to the creation of entropy. Okay, that's really what dissipation is. And as we will discuss in great detail, these equations of perfect hydrodynamics do not create entropy. They conserve entropy. Okay, adding terms here will allow entropy production in our system. Okay, so that's how you should think about dissipation. Good. Any other questions or comments? Excellent. So, what we now need to do is to try to understand what the allowed forms for pi mu nu and J mu dis are. Well, what are these allowed? What can we say immediately? Being effective field theorists, we immediately say, aha, this is constrained by symmetry. Let's try to work like we work in field theory. We've got some action. In the derivative expansion, we just write down every term in that action that is consistent with symmetries. And unless there's some very good reason to think otherwise, all these terms are allowed, not knowing the particular dynamics of our system. So let's try. This will turn out not to be enough, as I will explain, but let's start doing that. Okay? So let's start doing that with an example. So example, charged fluid in 3+1 dimensions at first order in the derivative. Okay? The first thing we're going to try to do is to try to constrain the equations of hydrodynamics to the extent that we can just from symmetries. So, I've said many things here. I've said charged fluid dynamics, by which I mean single charge. Okay? So everything I've written down is appropriate for this system. System is thermodynamically specified by a chemical potential, temperature, and velocity field. Okay, I've said first order in the derivative expansion, by which I mean I will only look at terms in J mu dis and pi mu nu that have one derivative, either of space or of time, I don't care, but one derivative overall, okay, and no more than one. Okay, I want to classify all terms that symmetry allows me to write, okay, for these expressions. Now this is a simple problem. This is not a difficult problem. Okay. However, we need to deal with a couple of important, if irritating, subtleties before we get the right answer. Okay, the first one is subtlety 1. The first subtlety is that T and mu are absolutely well defined. We know exactly what they mean, and u mu in equilibrium. But they have no God-given notion for processes out of equilibrium. By which I mean, I specify my fluid by saying that it is described by this temperature field, this chemical potential field, and this velocity field. And you say, no, I don't think you're right. I will specify my temperature field by your temperature field plus divergence of your velocity field. Okay? Now, if one or the other of our characterizations differs in equilibrium, we can tell who's right by just checking against the equilibrium value of the temperature of chemical potential. But if the differences occur just at terms that vanish in equilibrium, so that differ just in terms in the derivative expansion, there is no particular way of knowing who's right. In fact, the question of who's right is not well defined, apart from a caveat I will get to as we go along. It's not well defined because temperature is not something that's defined in a field theory. There's no temperature operator in the field theory. You cannot take a state and find the expectation value of the temperature operator, the chemical potential operator, the entropy operator. These things are not well defined. They're just emergent thermodynamic notions. Okay? So these fields here are well defined in equilibrium, but have no God-given notion outside equilibrium, and therefore the equations that you write down for your field theory have to have the freedom of field redefinitions. Okay? We must be allowed to use field redefinitions in the full equations of the theory. So T is equal to T plus delta T, where delta T is any expression built out of derivatives. And I'll talk about some small constraints on this later on. But right now you can take this. Similarly for mu and similarly for u mu. Okay? Now, so this is like a gauge redefinition freedom in our theory. We can change variables, and as in any gauge theory, there are two ways one could work. One can either work in a completely gauge invariant way, or one can choose to adopt a gauge. Both are useful for different problems, but for lack of time in these lectures, I'm only going to choose the second and calculationally more useful method of fixing a gauge. Okay? In fact, I'm going to fix a gauge that Landau fixed long ago when he started studying fluid dynamics, and in his honors called the Landau gauge. The gauge is specified by pi mu nu, u nu is equal to 0, and j mu dis, u mu is equal to 0. Now, what does this mean? You see, firstly, let's count how many gauge conditions we have. Capital D here, because one free index, 1 here. How many gauge degrees of freedom? Capital D plus 1, as many as the variables of hydrodynamics. So the numbers match. Now, what do I mean by saying that this is my gauge? What I mean is that, suppose I have a specification of the stress tensor that does not obey this condition. Then I'll make a field redefinition on the temperature field, which sits inside here, the chemical potential field, which sits inside here, and the velocity field, which sits here. This field redefinition will take what was the perfect fluid, for instance velocity, and convert it into perfect fluid plus fluctuation. So it'll take part of what was in the perfect fluid part here and transfer it into pi mu nu. Okay? And by this process we can adjust pi mu nu a little bit, and you can easily convince yourself that at least order by order in the derivative expansion, you can always use that freedom to set these gauges to make sure that these things are true. Is this clear? So we had this ambiguity of you know, when I started glibly by talking about a temperature and chemical potential velocity field, I didn't really know what I was talking about. With these definitions, I know exactly what I'm talking about. Okay, let me say this in a slightly more geometric manner, so that it becomes sort of clear what it is. Let's look at this pi mu nu u nu is equal to 0. What does it mean? If this is the case, then suppose I take T mu nu u nu. Okay, because T mu nu is T perfect plus pi, but pi dotted with u is 0, this is simply equal to rho plus p u mu u nu plus eta mu nu, so that's delta mu nu p into u nu. Okay, so now what is this? U into u gives -1 and u into delta gives u. Because of the -1, the p and the p cancel, so we get rho times u mu. Okay, so the frame condition pi mu nu u nu equals 0 can be stated more geometrically. It can be stated more geometrically in the following manner. Given a stress tensor, the velocity field is the unique time-like eigenvector of the stress tensor. Eigenvector where the stress tensor is just thought of as a 4x4 or capital D cross D matrix. Okay, and the energy density is the eigenvalue of that eigenvector. Okay, that plus the equations of thermodynamics helps you define the temperature, define exactly what you mean by the temperature. I emphasize this is an arbitrary choice. You could have chosen made other choices, and in fact there's another popular frame choice in the literature called the Eckhart frame. Mr. Eckhart decided to specify u mu by aligning j mu with u mu. Okay, by in fact setting j mu dis equals 0. Okay, there are various things you can do. I won't get into. There are various other frame choices you can adopt. It's like a gauge choice. I've adopted one convenient one, which I'll stick to throughout these lectures, though sometimes it's not the most convenient thing to do, but I'll do that through these lectures. Okay, any questions or comments about this gauge or frame ambiguity of hydrodynamics and our method of fixing it?
Why choose to fix the gauge at all? When we deal with Maxwell's equation, we want to keep the covariance
yes.
as long as possible.
You can, and this is sometimes useful. Okay, it's just that it makes things a bit calculationally easier if you don't. So in the papers I've written on the subject, and some I've not fixed and some I have fixed. For the purpose of these lectures, I'm going to fix, just because it's easier to present the formulas. Yeah. Okay. Other questions or comments? Yes, that's sometimes a very useful thing to do. Other questions or comments? Yes.
This U field has to be globally defined in order to have an equilibrium, so it has to be a globally defined time-like vector field, or?
Yes, I think in order to, I think so. I think you want a globally defined time-like vector field. That can, of course.
So in situations where you cannot define that in curved backgrounds, what will happen?
Well, let's look at a sphere, for instance. Okay, remember this is a 4 velocity. Okay, so if you've got, you see, we're not going to look. We're going to look at things where you've got a non-compact time-like direction, things happening in time. So suppose you looked at a 3 sphere. This might be a place where you might worry that you cannot define this vector field, but you can. It's just that the vector field somewhere goes to 0. The spatial component of it somewhere goes to 0. That just means that the fluid's at rest somewhere. Okay, if you've got a more serious obstruction than this, I would have to think about. I don't know of an example, but I'm sure you could come up with one. I would have to think about it. I don't have anything. Yes.
Does this delta t have to be small if like the derivatives are small?
What? Say again? That?
If the derivatives are small, like the of the fields.
Very good, very good. This brings me to a point that I did not say, though I meant to. And this is the question of yes. So delta t is small. That's true, but this is also small compared to this. because this is also made up of derivatives. So something that I should have, so you can always use self-consistently, some derivative term to kill a derivative term. But something I should have specified is, what is the derivative expansion and expansion in? The idea is that it's an expansion, at least roughly speaking, in the mean free path divided by length scale of variation. Okay? You saw why that's reasonable. We saw that this thing should only work in situations where everything varies on a length scale that's very large compared to the mean free path. When we start looking at this in the gravity context, we'll make the statement completely precise. It will turn out that in the simplest conformal situation, the effective mean free path is 1 over the temperature of the system. So hydrodynamics works if the length scale of variation at any given point is large compared to the local value of the temperature at that point. Okay? Good. So the expansion that we're talking about here is very much like an alpha prime expansion in string theory. There's a length scale where the length scale is the mean free path instead of alpha prime, and then you expand in derivatives. Good. Other questions or comments? Excellent. So let's move on. Okay. So we've dealt with irritating subtlety number 1. Okay. There is one more subtlety, or one more important thing to keep in mind before we get the right answers to the questions of what is the most general set of allowed values of the equations of hydrodynamics allowed by symmetry. And that subtlety is that if you write down an expression, suppose you write down an expression for pi mu, I write down another one, our two expressions differ, but only by terms proportional to a lower order equation of motion. Okay, so for instance, if we work in the first order in derivative expansion, your pi mu 1 and my pi mu 1 differ by terms that are first order, because pi mu is by definition first order. But this first order thing is just the expression that comes from the perfect fluid equations of motion, which you'll remember as first order. It's one derivative acting on a zero derivative expression. Then our two expressions will give us identical equations of hydrodynamics up to the order of derivatives that we're keeping. They will differ at second order, differ at one higher order than we're keeping. To the order of interest, our equations of hydrodynamics will be identical, because we're not, you see, if we're interested in these expressions for the stress tensor and the charge current only on solutions to the equations of motion, then expressions that differ by terms that are always zero on solutions to the equations of motion are identical. Okay? So when we are categorizing the allowed inequivalent expressions for pi mu and j mu dis, we should characterize these expressions up to terms that are equal by equations of motion. Now some of you are used to the fact that when we do field theory, these two irritating subtleties that I told you about are actually the same thing. Okay? You're used to the fact that in an action, a small field redefinition changes the action proportional to the equation of motion of the system. This is obvious, right? If you've got some action is a function of phi, then I do phi is equal to phi plus delta phi. The change in the action is del s by del phi times delta phi, but del s by del phi is the equation of motion. Okay? In field theory situations where you're dealing with something that comes from an action, within the action, just dealing with the ambiguity of field redefinitions is all you need to do. You don't need to do the second thing. But it's very important here, and we'll come across this many times, that the equations of hydrodynamics, at least the way I formulate them, are not written in terms of an action. They're written in terms of the equations of motion. Okay? And we come across this many times. Because of this, we need to account for both these subtleties independently. Okay, so now that we've got these irritating subtleties out of the way, we're ready to please.
But could you formulate them in terms of an action, and then you wouldn't have to do that?
Yes, if you could formulate in terms of an action, you wouldn't have to do that. The difficulty is that it's hard to formulate equations for dissipative systems in terms of an action. Okay? Now, I think that your point is a great one. Something like this should be possible somehow, but I don't know how to do it yet. But I think it's a great.
Excuse me, but your definition of dissipation was a qualified one, right? Like it was not energy leaking out of the system; it was redistributing. So it's not genuine dissipation. So
No, but in this dissipative system, any reasonable idea of the volume of phase space will shrink, because completely disparate solutions all tend very fast to equilibrium. Okay, and so phase space volumes will not be conserved with any reasonable notion of that. Okay, excellent. Other questions, comments? Okay, so now that we've got all our, all these subtle points clear, let's move to specifying the most general expansion for pi mu nu and j mu dis allowed by symmetries at first order in the derivative expansion for a charged fluid. So now we want to do some counting. Okay, one more thing I should say before we start. You see, at any given point in a fluid flow, you have an SO3, 1 symmetry. But this SO3, 1 symmetry is broken in a big way by the fact that the velocity field has a certain value at that point. That breaks it down to SO3. Okay? So, for purposes of the derivative expansion, SO3 can be thought of as being maintained by the background. I should have said SO little d, 1 and SO little d. So sometimes I lapse into thinking in 3 + 1 dimensions, which I know is heresy for a string theorist, but I'm sorry. Okay, excellent. So, so what we're going to do is to classify everything in terms of the SO. Okay, so for my counting purpose of counting, I'll assume we were in 3 + 1 dimensions. Okay, so it won't change very much. I'll classify everything in terms of symmetry transformations under the local SO3 that is preserved by the velocity field. Okay, so now let's start doing some counting. Suppose I've got the derivative of the temperature. That's 4 independent objects, because there are 4 derivatives. But I wanted to classify these as how they transform on the SO3. This clearly transforms as 1 + 3. Okay, for instance, if the velocity field at that point is 1, 0, 0, 0, then the time derivative is the 1, it's a scalar under SO3, while the space derivative is the 3, it's the vector under SO3. Okay, great. Similarly, del mu of the chemical potential is 1 + 3, and del mu of u nu, so this is a little more tricky, because you want to remember that u only has 3, not 4 components. The 3 components that are there transform like a vector. You're projecting out the path the change in u cannot be in the direction of u. So this, in terms of counting, is 1 + 3 tensor producted with 3, okay, which is equal to 3 plus 1 + 3 bar plus 5. Where 3 bar means a pseudo vector. I know that a 3 bar, in 3 × 3, you know that in a vector cross vector we get a scalar, a vector, and a tensor, but the vector is a pseudo tensor because you need an epsilon to make it. It's a cross product. Okay? Excellent. So now we've got all data in our fluid fields at first 1 derivative order and have classified them according to their transformation properties, the transformation properties under SO3. But remember, not all of this data is independent. Terms, expressions that differ by perfect fluid equations of motion should be set to 0 or are equivalent. Okay? So let's also count equations of motion. So del mu t mu nu, what is the counting? Well, this transforms as 1 + 3. This is clear. The part proportional to the velocity, the part perpendicular to it. Okay? And del dot j transforms as a 1. So now we list the available data. How many 1s do we have? So let's be clear, transformation, number, and then expression. Okay, so let's look at the 1s. Are there any 1? There are no 1 bars, so there's a 3, there's a 3 bar, and then there's a 5. Okay, so how many 1s do we have? Well, we had 1 plus 1 plus 1, but then I'm supposed to subtract 1 and 1. So the net number is 1. 3 minus 2 is equal to 1. Okay, on shell, board up. On shell, the number of degrees of freedom is 1. The number of inequivalent, on shell inequivalent scalars is 1. What about the vectors? So the vectors, well, we have, sorry. Yeah, maybe. Yes. Excellent. So we have 1 plus 2 is 1, so that's 2, plus 3 minus 1, so that's 2. Okay, and 3 bar, there's 1, there's no 3 bar equation of motion, and 5, there is 1, there's no 5 equation of motion. So these are the number of inequivalent expressions categorized according to their symmetry transformations built out of fluid fields. Now, I'm actually going to do better. You see,
Is there some assumption about the background symmetry? I mean, you explained it by saying that you boost the thing, and so you need to take the relative velocity, but it could be less than SO3. I mean, or is
the background, it's the tangent space symmetry that's relevant.
But that seems to be here also following from having Lorentz symmetry at some point, right?
Yes, so you have local Lorentz invariance,
Yeah.
but the value of the velocity field there breaks that down to SO3.
Right, but you could have started with less invariance.
Less in no, we just mean local Lorentz invariance. You see, okay, this is a very good point. So the question is, what if we're looking at a curved space? What if we're dealing with fluid dynamics, hydrodynamics in a curved space, or in the presence of background electromagnetic fields? Okay, this breaks the symmetry, and in typically such a situation, there is no symmetry left. However, and in fact, it's exactly the point I was getting to. However, you see, it would be inconsistent to have fast varying background fields and slow varying velocities. This would be inconsistent because these background fields enter in the equations of hydrodynamics, and if you've got fast variation in any of these background fields, it would induce a fast variation in the velocities due to dynamics. Okay? So the only way we can consistently talk about hydrodynamics is if all the background fields are slowly varying. In particular, the metric, so let's look at the metric as an example. The metric is slowly varying, its curvatures are slowly varying, which means in a local patch, up to derivative corrections, it's locally flat. Okay? So, for exactly the reason that Julian mentioned, we're now going to not be satisfied with counting just the degrees of freedom in the derivatives of the fluid dynamic fields. We will also count expressions that we can build out of background electromagnetic and curvature invariance. Now, the great thing about curvatures is that they're all second derivative. Okay? Of course, we preserve diffeomorphism invariance and everything. However, background electromagnetic fields are not. So you can turn out an arbitrary background electromagnetic field, by which I mean some classical background field that couples to the conserved U1 charge. Okay? And we should also categorize how that object splits under SO3. And it's a 3 plus 3 bar. For instance, there's 6 components in it. It splits in under SO3 times SO3 or SU2 times SU3 as a vector under one SU2 times a vector under the other. Okay? So here we should add a plus 1 here for the 3 and a plus 1 here for the 3 bar. So the total number here is, this remains 1. The total number here is 3. The total number here is 2, and the total number here is 1. Okay? So if we're interested in dealing with fluids that propagate not just in flat space without background electromagnetic fields, we need to include these guys on the same footing as fluid variables, because the equations of motion will mix them all. Okay. Now, let me, to complete this very simple and perhaps painfully detailed analysis, but just to have one example done in great detail, to complete this example, let me give you expressions for all of these quantities. Now, these expressions are not unique, because once I give you an expression, you can change the expression by adding something that's on shell 0. But I give you one example. So here I can choose the scalar to be del dot u. You could also add, for instance, u dot del of temperature to it. Turns out, you can use the perfect fluid equations of motion to express that in terms of del dot u. So it's sufficient to work with del dot u. Here, I will choose these to be the derivative of the chemical potential by the temperature, the electric field, and the derivative of the temperature. Now, in the derivative, I'm going to put a symbol P behind it, which means projected. So I should define, sorry, I'll go back to white. I should define this projector. So this pi mu nu is the projector onto the subspace orthogonal to the local velocity field. Projector onto space, okay, and is defined by u mu u nu plus delta mu nu. Okay, so every time I've got a vector field and I put a p behind it, I mean I multiply that expression by this object. Okay, so I project out the time part, project onto the part that's only in the spatial sections. Is this clear? Okay, excellent. So these are examples of the vector fields, yeah, okay, following the other guy, I should have written this as 3 minus 1 plus 1, okay? And this guy here can be thought of these, oh, and what is E mu? I should define that. E mu is equal to F mu nu times U nu. It's what the electric field would have been if U was along the time direction. Please.
Why do you choose to do the projection onto the just?
Because I want to deal with vectors.
Okay.
A 4 vector is a 3 plus 1, but I want to separate out the 3. Okay. The projector does that. Yes. And let me also define this quantity B mu, which Son Soroka have made famous. Okay, this is the 3 bar in F mu nu. Okay, so here, and I'll also define one more thing. I'll define omega mu epsilon mu beta u nu del alpha. This quantity you think of as the vorticity. Okay, it's the relativistic version of the vorticity of the fluid flow. Okay, so here omega mu and B mu are the examples of the 3 bar, and for the 5 there's sigma mu nu, where this is my last irritating definition. Times del alpha u beta plus del beta u alpha by 2 minus del dot u into p alpha beta divided by 3. Okay, it's the so what is the sigma? Sigma is a symmetric combination of velocity derivatives with trace removed and projected onto space. Okay, so this completes our counting, and so can everyone see if I write on this board? Can you people see that? Okay, excellent. So now we're ready to write down the most general expressions for pi mu nu and j mu dis. Okay, pi mu nu.
Can you not write all the way to the left?
Yes, yes.
Thanks.
So pi mu nu. Okay. Now, firstly, what is the symmetric content of pi mu nu? Symmetric content of pi mu nu is one tensor and one scalar. Remember that pi mu nu is defined by the Landau frame condition, so it's orthogonal to velocity. So it's just a tensor in the space directions, a 3 cross 3 matrix, which can be thought of as the 5 and the 1. Okay, so pi mu nu is an arbitrary and J mu this is equal to sigma into okay, J mu this was entirely a vector because of the Landau gauge condition. You project out the scalar from J mu. Okay, so what I've done is I've looked at this table. Pi mu nu has to be given by a tensor expression, the linear combination of a tensor expression and a scalar expression. The scalar, of course, in order to match up indices, you need to multiply the scalar by p mu nu. Okay, and J mu this has to be given by a vector expression. I've written down the most general vector that comes from this table. Okay, each of these unknown coefficients, eta, this guy is zeta, is that right? Some fancy Greek letter, sigma, alpha 1 and alpha 2 are arbitrary functions of chemical potential and temperature. Okay, so this is the most general symmetry allowed. This is the most general symmetry allowed equation of hydrodynamics. And this most general symmetry allowed equation of hydrodynamics depends on 5 unknown functions. 5 unknown functions of the temperature and chemical potential. Okay? Now some of these unknown functions have names. This guy is called the shear viscosity. This guy is called the bulk viscosity. And this guy is called the conductivity that appears in Ohm's law. Alpha 1 and alpha 2 do not have names. They don't have names because, as we will see in just a minute, alpha 1 and alpha 2 are forced to be 0. Okay? Symmetry is not enough to give us all constraints on hydrodynamics. There are other considerations which we will turn to very soon. Okay, so far I've assumed that my hydrodynamics preserves parity. If that's not the case, I can add 2 new terms. I could add plus, let's say, beta 1 times b mu plus beta 2 times omega mu. Symmetry allows 5 parity even and 2 parity odd unknown functions of chemical potential and temperature at first order in the derivative expansion. It will turn out, as we will see, that all except these three remain free, subject just to some inequalities. The remaining are all determined by other general considerations. Okay?
So what's the last term there?
Omega mu. That's this vorticity here. Okay, that's it for what we can learn from symmetry. It narrows down to equations to up to 7 functions. Symmetry in this context is not sufficient, and we're now going to try to understand what is sufficient as far as we know. Any questions or comments about this? Okay, excellent. So let's move on. Now, there are 2 efficient methods of imposing physical constraints on allowed expansions of the hydrodynamic expansion that I'm aware of. The first one of which was essentially, I mean, at least a basic idea, essentially pioneered by Landau and Lifshitz in their textbook on hydrodynamics, though they didn't always work it out right, as we will see. They made some mistakes. Yes?
Just very naively, pi mu nu, could you not add something like the symmetrized version of b mu omega nu?
Because that would, of u mu omega nu?
B mu omega nu.
That's second order.
Oh.
We're working the first order in the derivative expansion.
Okay.
Yes, so we can do many more things when we go to second order. I'll do the counting for you at some point. But, yes, you can't add u mu omega mu because that would violate Landau gauge. Okay, excellent. Fine. So, this first method was at least an essential idea and sometime in correct implementation, pioneered by Landau and Lifshitz. It demands the existence of a positive divergence entropy current. I'll turn to that, not as the first thing I do, because it's not the most conceptually simple thing. There's a much simpler conceptual constraint one can impose, which I'll first turn to. Okay, this stuff was worked out very recently, about 2 weeks ago, in a paper written by, one paper written by us, by Jyotirmoy, who's sitting here, Shayanthani, myself, Nabhamita, and Sachin. Is that it? Okay, and Tarun, yes. And another parallel paper written by Amos Yarom, Kovtun, Christian, and 2 other collaborators. I should have got the references. I'll give them to you. I'll give you the references tomorrow. I don't have them on me. Okay, and it's just such a simple thing, as you will see, and quite powerful. But it was worked out in 2012, which gives you an idea of how little people have really, in a theorist's manner, thought about hydrodynamics, as far as I can see. At least relativistic hydrodynamics. Okay, so the question, you see, in order to work out this constraint, what we're going to do is to switch to asking what sounds at first like a completely different question. Okay, we're going to ask a question in quantum field theory. So the question we're going to ask is this: suppose I start with a metric ds squared is equal to e to the power 2 sigma dt plus ai dxi squared plus gij dxi dxj, where sigma is equal to sigma of x, gij is equal to gij of x, and ai is equal to ai of x. And in addition to this background metric, we have a gauge field, which is a mu, which is equal to a0, ai, both of which are functions only of x. Actually, for later purposes, I should write this as calligraphic a0 and calligraphic ai, reserving the symbol actual a0 and ai to more useful fields. Okay, so what is this metric? This is the most general background metric which has a time-like killing vector field. Firstly, this has a time-like killing vector field, as is clear from the fact that every function that appears here is a function of x and not of t. So d by dt is a time-like killing vector field in this metric. It's also possible to show, it's easy to show, that any metric with a time-like killing vector field can at least locally be put in this form. So I've written down a background metric that has a time-like killing vector field. And I've written down a background gauge field that respects this killing symmetry. It's time independent. Okay? Now, the question I'm going to ask is the following. What is the partition function given a quantum field theory? I take that quantum field theory and I put it on this space. And I ask, what can I say about log z of the quantum field theory in this space, where z is defined as usual, trace of e to the power minus beta h plus beta mu q, where h is the conserved charge coming from the fact that I have a time-like killing vector field in my background metric. Okay, in the absence of funny anomalies, the charge current corresponding to this conserved charge is simply T mu nu times ukk mu, where ukk is the Kaluza-Klein velocity vector, which in this case is just 1, 0, 0, 0. Is the killing vector field. In this case is just 1, 0, 0. You can easily use the killing equation plus the conservation of the stress tensor to show that this is a conserved current. Okay, so that's why I've chosen a background with a background killing vector field. I've chosen it so that there is a conserved charge, the charge of energy in my system. We also have the conserved charge, the charge of the charge corresponding to the U1 vector, the U1 global symmetry in our system. So this quantity is some well-defined object. Well-defined can be computed in any quantum field theory. I'm going to ask what I can say about this partition function. Now, given
This J mu is not this J mu.
no, this is J mu energy. I'll never use this J mu. You can forget about it. Okay. Yeah. Now, of course, if I gave you a particular field theory, let's say n equals 4 Yang mills on this background, you would have to do a serious computation to find the partition function of the system. Okay? But I'm going to ask something much simpler. I'm going to ask, knowing nothing about the quantum field theory, what can I say on general grounds about what this partition function can be? Okay? In a derivative expansion in space, assuming that these AI, sigma, Gij fields are all slowly varying. Okay? I'm asking this question in derivative expansion because we're going to be able to use the answer to this question to get information about hydrodynamics, and hydrodynamics is worked out in a derivative expansion. Okay, so now this is a terribly simple job, and let me immediately answer it for you at first order in the derivative expansion. Well, let's first do it at 0th order. See, at 0th order in the derivative expansion, you see, we can forget about variations of fields. Now, there's something that you can immediately argue. That's sort of totally obvious, and that you can immediately argue, and that is the object T naught and sigma without any derivatives cannot appear independently in the answer to the partition function, but must always appear in the combination T naught times e to the power minus sigma, and similarly A naught must always appear along with the chemical potential and sigma in the combination well, actually this part. Okay, that T naught and sigma cannot appear independently, but have to appear in this combination. A naught and mu naught cannot appear independently, but have to appear in this combination.
Sigma is your conductivity.
Sorry, no, sigma is this sigma. Sorry. I'm sorry, I'm very sorry. Okay, what? Let me change this.
That's fine.
Phi. Okay.
Here.
T0 is 1 over beta.
What?
T0 is 1 over beta.
T0 is 1 over beta. T0 is 1 over beta. Yes. T0 is 1 over beta. And this is mu naught. Okay. Now, how do you make this argument? In order to make this argument, you use the fact that this form of the metric is preserved by some coordinate transformations. A simple coordinate transformation that preserves this form of the metric is just a rescaling of the temperature. Okay? Now, the partition function of our system, once we move to Euclidean space, is simply the path integral of our system on a temperature of size beta. But by making a coordinate redefinition, I can change the temperature of size beta to temperature of size 1, circle of size 1. But that coordinate change effectively shifts phi, okay, so that this combination is invariant. It's easy to check. Okay. Similarly, mu naught in this Euclidean space version of the partition function is simply the twist of any charge field as you go around the circle, and in the usual way is equivalent to adding a background gauge field, so that only this combination can appear, not mu naught and A naught independently. Okay, now just this immediately tells us the answer to what the partition function must be at 0th order in the derivative expansion. Okay, we use the fact that we know that in equilibrium, in flat space where nothing is changing, the partition function, this log z, is simply the pressure as a function of T naught and mu naught divided by T naught. Okay, this is thermodynamics or statistical mechanics, and if you've forgotten it, it will take you 2 minutes to derive it. The pressure is minus the free energy. Okay, we know this is true in equilibrium, but we also know that these guys cannot appear independently of sigma and A0. So this statement plus this statement tells us that in general the pressure is given by, and coordinate invariance is given by d3 d3x e to the power minus sigma by T naught. Pressure as a function of T naught e to the power minus sigma and A0 plus mu 0 e to the power minus sigma phi. This e to the power minus phi is simply the fact that the local value of the chemical potential, okay, after we move to a coordinate, a t coordinate in which locally at that spot phi is 1, is given by this object. Okay, or another way of saying it, the chemical potential divided by the temperature is the net twist as you go around the circle, and you can check that this gives you the right value. Okay, so zeroth order and the derivative expansion, this must be our partition function. Okay, this must be our partition function, and it's very easy to check that this statement is equivalent to the statements about perfect fluid hydrodynamics that I made 20 minutes ago. How do I check that? In order to check that, what I have to do is to take this partition function. Okay, so given a partition function, the question I'm going to ask is, how do I compute the stress tensor and the charge current that follows from this partition function? Okay, so oh, by the way, before I say that, you know, what is this saying physically? Physically, what this is saying is that at zeroth order and the derivative expansion, if we've got a system in equilibrium, okay, it's locally equilibrated, but at a local temperature value. So this is like T of x, the local value of the temperature, which has a redshift factor. Okay, and a local value of the chemical potential that is shifted by A0 and has a redshift factor. Okay, it's a physically very reasonable statement. You know, it's for instance the fact that air grows cooler as you go up. It's, you know, that kind of statement. Okay, a physically very reasonable statement that all of us are familiar with in one guise or another. Okay, so now there's a consistency check I can make of this of this statement that I'll tell you about just in words so that we can speed up. Look, given this partition function, we can look at the derivative of this partition function with respect to the metric. That gives us the stress tensor of our system. Okay, we can look at the derivative of the partition function with respect to the gauge field. That gives us the charge current of our system. Now we get some expression. I compare that to the expression of perfect fluid hydrodynamics, in which I substitute the temperature by T of x and the charge density and the chemical potential by this quantity, and these two expressions match. I'm not going to work this out for you, but I'm assuring you that they match. Okay, this little exercise also gives us another consistency check. On the idea that in equilibrium T behaves like T of x and mu behaves like mu of x. Why does it give us this consistency check? It gives us this consistency check because what I've told you already implies that this configuration obeys the equations of hydrodynamics. How does it imply that? It implies that because I've told you that this configuration with this value of T of x and mu of x is obtained by taking an action and differentiating with respect to a metric and a gauge field. Now any expression, any coordinate invariant expression, when you build a stress tensor out of any coordinate invariant expression by differentiating that expression with respect to a metric, that stress tensor is automatically conserved. That follows from diffeomorphism invariance. Similarly, a charge current built out of differentiating a gauge invariant expression with respect to the gauge field is automatically conserved. Let me remind you of why that's true in the case of the charge current. Suppose I've got some action, A mu, and I find a current from it, so I get del S by del A mu. That's my current. Okay, now if I looked at the variation, this gives me this times delta A mu, okay, is the variation with respect to an arbitrary variation of the gauge field. But if that variation happens to be a gauge transformation, that's del mu of phi. My gauge invariance is 0. Let me integrate by parts. That tells me that del mu of del S by del A mu is 0. Okay? So whenever I got an expression that is gauge invariant, I differentiate with respect to A mu, it gives me a conserved current. So the fact that this configuration, okay, that the stress tensor obtained from this configuration and the charge current obtained from, from this action, and the charge current obtained from this action, differentiating it with respect to a metric field and a gauge field, agrees with the perfect fluid stress tensor with this configuration, and the perfect fluid charge current with this configuration tells you that this configuration obeys the perfect fluid equations of motion. Okay, I know that sounds like sophistry, but it's not. It's okay. Okay, fine. But we're not going to waste time on the perfect fluid. Please.
Where does the small alpha in your metric enters and all that?
Alpha.
Small alpha of x or a.
Sorry. A. Good question. So far, it hasn't entered at all. It hasn't entered at all. Why? Because AI is not gauge invariant. Okay? The most general expression that you can write here has to be something that is gauge invariant under Kaluza-Klein gauge transformation. Let me talk about that immediately. Thank you. It's a good question, something I should have spoken about. You see, there's another invariance of this metric that we have not made explicit, and that is invariance under coordinate transformations of the Kaluza-Klein form. For those of you who haven't realized, of course, all of you have realized, but anyway, this metric is of the Kaluza-Klein form. Okay, you open Pulchinski and Kaluza-Klein, you'll have written down this metric, except you'll have called this sigma, not phi. Okay. Okay. So there's another famous invariance of this metric. And what's that invariance? It's t goes to t plus theta of x. If you do this along with ai goes to ai minus del I theta, this metric is unchanged. Okay? This tells you, since we want our answer to be coordinate invariant, our answer has to respect this gauge invariance. So it tells us that the answer cannot depend on AI alone, okay, but can only depend on gauge invariant combinations of AI, and therefore, morally speaking, on Fij, though I'm just going to tell you that there's an exception. Okay, so 0th order in the derivative expansion, there's nothing else we could have written. Now let's move on to first order.
Do you need to state that phi should have restrictions in how it varies?
It has to vary slowly. Yes. Everything has to vary slowly. Everything here is slowly. Okay.
But they are all independent time.
What?
Your background is just depending on space.
Space.
So your fluid dynamics gives you time independent.
Yes. So fluid dynamics, all we're going to generate from this is equilibrium in fluid dynamics. Okay? So we're going to get constraints. You know, the point is that what we're going to do is to get constraints on the general equations of hydrodynamics by demanding that they admit good equilibrium solutions. That already constrains things in a significant way, as we'll see. Okay, so let's move on. So now we've got this, we want to write down the terms at first order. So let's look at first order in the derivative expansion. What do we have? We've got a derivative of this phi field. We've got a derivative of A0. Okay, notice that we're only going to allow gauge transformations that depend on space and not on time. Okay, so A0 is gauge invariant. Okay, a derivative of A0, and well, anything we can build out of the metric is second order because it's curvatures. From AI, we can build Fij, which is del I Aj minus del J Ai. And now we want to change the partition function. But the partition function requires a first order scalar. Doesn't look like we have any first order scalars. So it sounds like just on symmetry grounds the partition function cannot be corrected at first order in the derivative expansion. This is too fast. It can, but you have to think a little bit about how it can be corrected. Maintaining gauge invariance, there is a 3-parameter set of allowed corrections. The 3-parameter set of allowed corrections is C1, A dA plus C2 A dA plus C3 A dA. The three Chern-Simons forms. The three Chern-Simons forms that you can build out of two vector fields. This is a Chern-Simons term built purely out of the spatial fields. Chern-Simons term built out of the Kaluza-Klein gauge field and mixed Chern-Simons term. Okay? Though these are not built out of field strengths, as you well know, these are perfectly gauge invariant, provided C1, C2, and C3 are constants. Okay? So there is some ambiguity in what you can write down in your first order action. There is some ambiguity in what you can write down in your first order action. However, this ambiguity is not parameterized by new functions of A0 and phi. Sorry, new functions of A0 and phi. It's just parameterized by numbers. Okay, pure numbers. When should I be finishing? 10 minutes.
Yeah, 10 minutes.
Okay, it's just parameterized by pure numbers. Okay, so now, okay. Now there's one more thing that I want. Okay, let me say this one more thing before we proceed. So far, I have assumed that the gauge symmetry. Okay, firstly, immediately I should say that if we're insisting on a system that maintains parity, C1, C2, and C3 are all 0, because all these terms obviously violate parity because of the epsilon symbol. Okay? Now there's one more thing I should say here, and this other thing goes as follows. If we want to insist, so far I've been insisting on dealing with systems that really maintain gauge invariance, even in the U1 gauge invariance of this big vector field A. Okay, even in the presence of a background gauge field. But suppose we're studying a system which has a U1 cube triangle anomaly. Okay, suppose we're studying a system that has a U1 cube triangle anomaly, then the equation del mu j mu equals 0 is replaced by an equation which is del mu j mu is equal to some number times star of f wedge f. So that number is minus c by 8 in my conventions. Okay. Now, the action that we have written down is too limited to account for such an anomaly, because the action we've written down is gauge invariant, and therefore, as I explained to you, any charge current that follows from it is automatically conserved. Okay? So in order to allow for such an anomalous term, we need to write down a non-gauge invariant contribution to the action. Okay? And the question is, can you do it? Now, at first you might think that this is certainly not possible in terms with, it should not be possible on general grounds to be able to write down a local counter term whose gauge variation provides the right hand side needed to remove the divergence of the current due to an anomaly. Because if this were possible, then given an anomalous theory, you could modify your theory by adding the relevant counter term and would be non-anomalous. Okay? Anomalies are precisely those obstructions to writing down a gauge invariant partition function that cannot be removed by adding a non-gauge invariant local counter term to your action. However, I'm not interested in removing this anomaly for all processes in the theory, just for the processes in equilibrium. And in this case, it turns out quite beautifully that it is possible to write down a gauge invariant term, a gauge non-invariant local expression that produces this anomaly. And that expression is simply A0, some number which I'll tell you about, but A0 times AI ADA. I'm only writing a 3-dimensional action. Everything is a 3-dimensional action. You see, because we're writing a partition function as a function of 3-dimensional fields. Phi AI, Gij, all three-dimensional fields. Okay.
So I just can't read what's curly and what's not curly.
Okay. This is not curly. These are curly.
Okay.
Yeah, I'm sorry about that.
Okay.
Yes.
What's the difference between curly and not curly?
Okay, I've not defined not curly yet. So far everything is curly. I'll define not curly. Okay, let me immediately tell you about not curly since the questions come up. You see, there's something that's not nice about this curly field. And that is, it's not Kaluza-Klein gauge invariant.
Can you lift the board, please?
Lift the board. Okay, so just as an aside, let's do a little exercise in Kaluza-Klein gauge transformations. Okay, suppose I do the coordinate change, t goes to t plus theta of x. Under this coordinate change, we're now going to work out how 4 vectors with upper and lower indices transform. Okay, I'm going to leave it as an exercise for you to show that given an arbitrary 4 vector, the upper I indices and lower 0 indices are Kaluza-Klein gauge invariant. Do not transform under this coordinate transform. However, lower I indices and upper 0 indices are not Kaluza-Klein gauge invariant. They do transform under this coordinate transformation, and in fact, that transformation is given by bi goes to bi minus del I theta times b0, and b0 goes to b0 plus del I theta bi. Okay, just using the usual coordinate transformation rules apply to this particular coordinate transformation, you get these formulas. Okay, this applies to any object with lower I indices, in particular applies to curly AI. Okay, so expressions that are written in terms of curly AI, while can be, this expression here, for instance, all these expressions here are manifestly, well, these expressions, for instance, are curly AI gauge invariant, are ordinary U1 gauge invariant. They're not manifestly Kaluza-Klein gauge invariant. But there's a way of fixing this. There's a way of fixing it, defining a non-curly AI field, which is curly AI minus A0 times AI. Okay, and you can check, well, it's obvious from here. See, you know what the AI transformation is. AI goes to AI minus del I theta, and you can check that this object is Kaluza-Klein gauge invariant. It's sort of obvious if you stare at it. Okay, so as we move on, I will write all expressions in terms of capital AI rather than curly AI, so that I can make things manifestly curly, Kaluza-Klein gauge invariant as well as. It's an irritating complication, which I will gloss over much of the time. Okay, very good. So let me quickly get to the point here. You see, this expression here is not gauge invariant. Why is it not gauge invariant? It's not gauge invariant because while f in ADA is of course gauge invariant, this is not. Under a gauge transformation, it changes. This A here changes by d of chi, where chi is a function. Now, we can try to use the usual Chern-Simons trick of integrating by parts to move the d onto this and this. Moving the d onto this gives us nothing because d square is 0. Moving the d onto this gives us, so change under gauge transformation gives us C dA0 wedge dA times a number, maybe minus C. But remember, we're only interested in configurations which depend only on space. For such configurations, you can easily convince yourself that this expression is proportional to f wedge f. So there's a factor of 8 between this and f wedge f. Okay? So adding such a counter term here exactly produces the gauge variation, the variation under gauge transformation needed in order to produce the anomaly. Let me remind you why there's any connection between an anomaly and a variation under gauge transformation. I've reminded you of this already, more or less. Let me remind you again. The variation of the action under an arbitrary change of A mu is J mu times delta A mu. When delta A mu is pure gauge, it's J mu times del mu of chi. Integrating by parts, you get del dot J times chi. So if you know that del dot J is equal to F wedge F, then the variation of the action must be equal to F wedge F times chi. So we're searching for an action whose variation under gauge transformation is F wedge F times chi, where chi is the gauge transformation parameter, but I've just shown you that this term in the action does the job. Okay? So now we're through. For an arbitrary first order system, charge system, including systems that have a U1 cube anomaly, we've written down the most general form of the partition function up to terms of first order and derivatives. Okay? There is a term whose form is dictated by the U1 cube anomaly, and there are 3 other constants in the game. 4 constants, one of which is an anomaly, 3 of which are at the moment uninterpreted. The most general one derivative partition function. Okay, now some of you are wondering, my God, this is quite dichotomous. We started by talking about fluid dynamics, and then we moved to talking about what partition functions. Now, of course, the reason I've done that is I'm going to now constrain the equations of fluid dynamics, okay, by demanding that the results you get for the stress tensor and the charge current obtained out of this action by differentiating it with respect to the metric and the gauge field agree with the results that you get from hydrodynamics. Please. We'll do that tomorrow. Okay, and that will tell us something interesting. It will tell us that alpha 1 and alpha 2 are 0. It will not tell us that beta 1 and beta 2 are 0, but will determine the functional form of beta 1 and beta 2 as a function of temperature and chemical potential in terms of thermodynamic quantities and these constants C1, C2, C3, and C. And in special cases, we'll agree with the results of Son and Soroka, who asked the same question, but using the more traditional Landau entropy current analysis, as I will explain to you tomorrow. Okay, thank you.
We have time for some quick questions.
So the U1 cube anomaly arises in theories with fermions. There is no fermion here, right? Or
well, I haven't told you what kind of theory I'm looking at. You see, I could be looking at n equals 4 Yang-Mills, which has fermions. Okay, it doesn't matter. The long distance description is hydrodynamics, independent of what your short distance description was. Might have contained fermions. I'm allowing for that possibility. As an example of a system to which hydrodynamics applies and does have fermions is n equals 4 Yang-Mills. Because that's the example from which all this started.
If I look at the special case of your recent argument, where phi equals 0 and Gij equals 0, only Ai non-zero.
Gij constant.
Yes.
Yes.
That basically Einstein's argument, right? That gives you diffusion constant equals conductivity.
Exactly.
Yeah.
So that this guy being 0 will be Einstein's argument.
Right. Okay.
Okay.
So
and this being 0 will be something sort of similar.
So
This coming out will be sort of new.
No, of course, there's a lot of new things, but
yes.
We can. Now let's just talk in terms of positive entropy production.
Yes.
Einstein says, well, equilibrium should be a solution. That was his condition.
Exactly.
Which is what you're.
Which is exactly what we're doing, but in a systematic manner that will allow you to generalize to higher orders and so on. Exactly. So the basic physical idea is that the equations of hydrodynamics have to be not so general that they do not allow equilibrium in situations in which equilibrium must exist. That's the basic idea. So that constrains these equations.
Can you turn it around and prove positivity of entropy production, starting from the other?
So to first order in the expansion we can.
We can, okay.
As I will explain. Yes, but modulo some inequalities. I will explain this. We don't yet have an all orders proof or a counterexample to this to the statement. Though there's an interesting complication when you deal with superfluid hydrodynamics, as I will also explain. That's a very important and very interesting question. The question is, can you demystify all these, well, you don't even know the arguments, so it's not mystical to you, but there are mystical sounding arguments about dealing with positivity of entropy production. That sounds deep, because Wow. Can you demystify them by relating them to much simpler things like this lowbrow stuff? I don't fully know the answer, but I'll tell you the answer to the extent that I know it.
Okay, let's thank Shiraz again.